how's this then? I unmuted the wrong thing. I unmuted the webcam instead of the microphone, and my webcam doesn't support sound. So, all right. So once again, welcome to Automata, Computability and Complexity. I see my microphone is in the red a little bit. Let me turn it down a tiny bit. All right. There we go. Good. Yeah, welcome back. Let's see if we can make this work again today. The feedback fruits links for today is on screen, but as Otto has just demonstrated, you can also get it in chat by typing !FBF. Please make sure to join us there. Today we'll be talking about a couple of different topics: countability, a bit of a recap of what we already discussed in reasoning and logic, undecidability. So last week was all about these decidable problems. This week we're going to talk about undecidable problems, problems that have no solution. And we're going to talk a little bit about reductions. And if time allows, and I think it should, we will also talk a little bit about something called Rice's theorem. Now, Rice's theorem accidentally wasn't in your material to prepare, so I'll make sure that our slides about it are available later on. I've included a slide here, and I'll explain a little bit what it means so that we can practice with it today. But before we begin, any questions about the course so far? So I see two coming in already. So let's start with the one from SC Arcade. Are you also recording? Yes, I am also recording, and a replay will be available on YouTube. As for Otto's question, is this still material for the TI code course? Yes. So today is still for both course codes. Next week will only be for the CSE course code. Arcade, it's my YouTube channel, but again, I'll link them also in Brightspace. Last week's recording is also linked in Brightspace, so you can find it through there. Quirky, you're asking about the exam. At the moment, I have no update for you. As soon as I do, I will let you all know. And for now, what I've been saying for complexity theory, and the same holds here, Matthijs and I will make sure we have an exam ready at the currently scheduled date. We encourage you to make sure you are ready to take an exam at that date until further notice. I can imagine stuff might change over the next few days, but until then, we will prepare an exam and we suggest you prepare the materials. Otto, clarity on choosing the end term. Yes, pick whichever one you like. I will give all of you a grade for the CSE course code, but Osiris should make sure that this gets transferred to the TI course code if that's in your program. So I've been assured that you can pick whichever one you like. Lighting, you're asking about the midterm. The midterm grading hasn't started yet. I've been very busy with all kinds of other shenanigans that had to be dealt with over the last few days. I'm currently trying to set something up so that me and the TAs can grade from our homes instead of having to come to the same physical location. But I'm sorry to have to ask you to be a little bit more patient on this. We're working on it, but I cannot give you an ETA at the moment. Amida, is it possible to include the chat in the recordings? I'm sorry, but I'm a bit hesitant to do so. This morning, with a first-year course, chat got really out of control. I'm hoping and trusting that this will not happen with you, but I'm not confident yet recording it. I'll try to state questions out loud if I think they're useful and answer them on stream, so that hopefully that can help, but we're not recording them yet. Final question from Zoom, and then I suggest we get started. Are we going to be able to submit our assignments for next week? So as announced yesterday, again, we're dealing with one situation after another, and lectures were a higher priority for now. We hope to have a system set up that we can use next week so that at least the TAs can give feedback, but hopefully you can also give peer feedback. But lectures for now are a little bit more important to us. Smorky, will we publish answers for the midterm? Yes, as soon as we're done grading. Default policy applies there. All right, then let's try to get this started. If there's more questions about the course, feel free to ask them. I'll try to sneak in answers later, but let's get started with some questions as well. So, first topic for today, countability. Now, this is something we also discussed already in reasoning and logic. So let's see how much of that you remember. Here we go. Of course. I always forget. Before we get started with questions about countability, let's hear a little bit how this lab assignment's going. The question is open in feedback fruits. Five more seconds to give me an answer if you haven't already. And let's see. No, not yet. All right. Seems you are also busy with other stuff for now. Then about last week's assignment. Let's see if that requires any changes for next year. Again, Feedback Fruits is happy to have your answer. Okay, let's take a look at that too. Okay, many people not participating in the lab. It's a pity. I realized that this week we also didn't really have a good solution for you, but trust me when I say that practice really makes perfect for this course. So I do recommend you check out assignment 6, especially these reductions, which are also crucial when we talk about reductions in the context of complexity theory next week. I really suggest you take a look at them to practice with them a bit. Even if we don't have a system set up, although we should have by next week, but even if we don't, you can always check your own answers. Really try to do these exercises. All right. Now then, let's talk about, okay. It's 3 questions. I forgot again. So finally, let's see if you prepared for today. So there were some videos to watch, some book chapters to read. Okay, 10 more seconds to give me an answer if you have one. And let's see. Okay, so people put at least in a little bit of time. Good. If you watched all the videos, and I guess you're in answer E at least, right? Answer D, maybe also read some of the book. Good. That looks promising. All right, let's give this a go then. So finally, our first topic, accountability, the recap of reasoning and logic. So let's see. Here we have 4 possible functions to choose from, and I'm wondering which one is not injective but is surjective. Let's see if you can find it. Feedback Fruits is happy to hear your answer. This should also work, but let's see. Yes, there we go. All right. Okay, and let's see. So 46% for answer B, and then a nice division over C, D, and E. Okay, so we are all in agreement that answer A is not the right answer. Can anyone tell me why that is? So why is A not the right answer? It's both surjective and injective is one of the answers given. It is bijective. Well, let's take a look. So what does injective again mean? That for different values of x, we get different values of fx. Well, that's the case here. So it is injective, which is problematic because we're looking for something that's not injective. And it should be surjective, but indeed it's not. As SEV points out, we don't hit, or well, we don't get to 0. So indeed, there is no x such that f of x equals 0. And therefore, this function is not surjective. So it is injective, but it is not surjective. Now, let's not do this for every answer. So let me discuss answer B, and then you can prepare your answers for answer C. So answer B, we take x minus 1 if x is larger than 0, and we take x equals 0 if x is 0. Well, notice then that for x equals 1 and x equals 0, we map to the same value. So this thing is indeed not injective. And is it surjective? Well, we can map to 0, and we can map to any number larger than that. We'll just take the number we want plus 1, right? So if we want to map to 8, then we take f of 9. So yeah, this thing is not injective, but it is surjective. Now, Ik ben altijd wakker is asking us a good question. Sipser has a different definition of n, right, where 0 is not in it. Well, just like in reasoning and logic, we usually say 0 is in it. This is something that no one is ever consistent on. And so, although this is an old exam question, we are now very careful about including this notion of n in an exam. And usually we try, we try to make sure that it doesn't matter whether 0 is in it or not. And as both Otto and Rickert are pointing out here, if 0 is not in n, then for answer A, we would run into the same problem with 1, right? So if 0 is not in it, then there would be no x such that f of x equals 1. Does that make sense, Wakker? In the meantime, you can tell me why answer C is incorrect. So for the record, B was the correct one, right? It was not injective, but it is surjective. So why is C incorrect? Alinson, yes, taking the root of a natural number is not guaranteed to be a natural number. Exactly, so let's make that even more specific. So let's take f of x equals 5. We cannot find a natural number x such that f of x equals 5. Pathon is giving us more examples, right? 5, 17, 31. Anything that's not a square we cannot map to. So yeah, exactly. It's not surjective. That's the problem there. Well, and D, I'll do that one again. It maps only to 0 or 10, meaning that, again, there is nothing that maps onto 5 or to 21 or to 42, right? This thing is also not surjective, is the problem with D. So that gives us B as our right answer. Then let's try, or a very quick recap for the people that picked C and D perhaps. So surjective, right, means that for everything in the codomain, we have a value in the domain such that f of a, such that when we execute the function on that value of our domain, we get the value in our codomain. So we map onto everything in our codomain. Injective is that for different inputs we get different outputs, simply put, right? So f of a does not equal f of b when a does not equal b. And finally, bijective is when it's both surjective and injective. Again, this should all be reasoning and logic stuff, but I realized that's 1.5 years ago, so some recap might not hurt. Okay, then there's also this notion of countability. So which of the following is a correct definition of a countable set? Let me see if I can make this work again. There we go. And Feedback Fruit is happy to hear your answers. And let's take a look. All right, overwhelming majority for answer C. Well done. So yes, what do we want? Well, we want the set either to be countable, right? Or we want there to be a bijection, one-to-one relation between our set and n, because n is the one that we've defined as a countable set, right? We can list all of the elements in there, even though there are infinitely many. And any bijection from n to another set means that other set is also countable. However, it is impossible to make bijection between a finite set and n, because n is infinite, but any finite set is also countable. So that is a crucial part to add to this definition, and answer C does so nicely. Okay, let's continue. So answer C was the right answer. Then let's go for a specific set. So here we go. Is this set countable? And once again, let's take a look. Overwhelming majority for countable. Now there were some questions about what this A is, right? So some people asked this in chat. A is just the letter A, right? So B is a set of strings, namely the empty string, assuming that 0 is an element of n, the string A, AA, AAA, and so on and so forth. Is that countable? Well, as Wakker explains to us in chat, yes it is. It has the same size as n. How do I know? Well, I can make very easily a bijection from n to this set B, right? 0 maps to the empty string, 1 maps to the string A, 2 maps to the string AA, 3 maps to the string AAA, and so on and so forth. So we can indeed construct one of these bijections, and therefore this set is countable. Okay. Let me open up the next question, but if you have any questions about this one, please do ask them. Meanwhile, the next question is available to you. Here we go. So now we have a set C. Is that set uncountable, is the question. Okay, so let's take a look at what you think. Overwhelming majority for no, not uncountable. Therefore, this set would be countable. Let's see if anyone is explaining already why. Yeah, so Taylor and Quirky are both giving us the right answer here, right? So Quirky is remarking that it seems very similar to the set of all fractions. Taylor's being perhaps a little bit more specific and saying, yeah, well, it's easy to construct a bijection from this to n times n, right? Again, what could we simply do? Well, 0, 0 maps to the empty string, 0, 1 maps to the string B, 1, 0 maps to the string A, 1, 1 to AB, and so on and so forth. So this would indeed be a way to show that there is a bijection from n, or from C to n times n, and n times n has the same size as n, and therefore this set is also countable, right? There's a bijection from n to n times n. So that is similar indeed to how we show that Q is a countable set. Alinson is asking, would AB be in the codomain? No, it would not. This is a set of A's or string of A's followed by a string of B's. Zoom Zoom and Frosty or Frostbite, you are both you both seem to imply that we could use diagonalization to show that this set is countable, but remember, diagonalization is only a technique to show something is uncountable. So that wouldn't quite work here. All right, let's move on to the next question. So no, this one was not uncountable. It is countable because there's a bijection to n times n, which we can map to n. Okay. 2 more of these. So once again, here we go. All right, so let's take a look again. Okay, a little bit closer together this time, less of an overwhelming majority, and also 101% answered this question. So let's see. Suppose we have the set E that consists of the sum of two rational numbers. Is this set uncountable? Well, the correct answer is again no. Why is that? Well, Q is countable. So we could again make a bijection from E, from E to Q times Q, or even just to Q, and Q is countable, therefore E must be countable. So yeah, Pathon is giving us the right answer, right? It's countable because we know the sum of two rationals is rational, and rationals are countable. Yeah. Okay, there was some discussion about is 1 minute not too long to answer these. I think it's going to be okay, but we'll see how this goes as we progress. Okay, last one on this topic of sets of just numbers. We will have one more question about a set of functions in a second, but first we have a final set F, x over y, where x and y are reals. Is this set countable? Okay, half a minute seems a bit overkill now. So if you've looked away from your screen because it says half a minute left, I suggest you start looking again. I've also configured hotkeys, so I should now be able to do this. Yeah, that will help a lot in resetting the timer later. So answer B, by far the most popular. Is the set countable? No. Why not? Well, because R is uncountable. Right, so this contains a number of real numbers, arguably all of them, and the set of real numbers is uncountable. Exactly, Zoom Zoom is saying the division of real numbers produces a real number, and that's not countable. Okay, how do we know? So this is a question about the previous one. How do we know we can make a bijection from E between E and Q? Well, notice that E still only contains fractions, right? Only rational numbers. So x plus y, that's great, but that's just a fraction, just a rational number. There's nothing fancy about it, okay? It happens to be a composition of two numbers, but x plus y is just one number. It doesn't matter that we can take multiple x and y's to get to the same output, because the set E is a set, so there's no duplicates in there, right? The number a half will occur in there exactly once. The fact that we can create it by using multiple x and y's, that's fine, but that's irrelevant. It only occurs once in the set E. And remember for you, Otto, that integers are also still rationals, right? I'm not sure if that answers your question, but okay. All right, let's move on to the last one about this. So we have two sets, H and I, and I wonder which of these is uncountable, if any. And Feedback Fruits is open now. So let's take a look. Answer D is by far the most popular, 68%, but well, a good third of you are spread over A, B, and C. So let's start with a question that Jonathan asked, right? What's the difference between H and I? So the difference between H and I is that H contains exactly one element, namely p to the power some constant, where the constant is an integer, and I contains all of the powers of pi for 0 and up. So positive integers including 0, right? So non-negative integers. Okay, we finally got there. So it contains pi to the power 0, pi to the power 1, pi to the power 2, pi to the power 3, and so on and so forth. Whereas H, indeed, as many people have pointed out, contains just one element. Well, if it contains only one element, it's finite, and therefore it's countable. So H is definitely countable. And I, again, there is a bijection from n to I, namely for 0 take pi to the power 0, for 1 take pi to the power 1, and so on and so forth. Indeed, Quirky has also put it, right? Pi to the power x is simply a bijection, proving it's countable. So the reason this question is in here is because many people often trip up between the distinction that a set of countable numbers cannot contain any real numbers, right? But it definitely can. Pi is a real number, and it can be in a countable set, right? If it's in a finite set, like in H, there is no issue. And if it's in I, then I completely lost my train of thought. This is the problem with just talking to a screen. H is a countable set, that's not an issue. And for I, we can make a bijection from n to I, even though the elements of I are real numbers instead of integers. So I is indeed infinite, but countably infinite. What is the element in H? I don't know, depends on what n we pick. So it has an element that is pi to the power n. Reals are indeed closed under plus, minus, star, and division, except for dividing by 0. Yes, so real numbers are defined, or rather rational numbers are defined as anything that we can write as a over b with a non-zero, and the rationals are a part of the real numbers. Lich, do we always use powers to imply repetition? No, so it depends on what we're using it on, right? If we're using it on letters, so the letters A, B, and C, for example, from some alphabet to form strings, then it implies repetition. In this case, we're using it on the mathematical number pi, and so it's simply a power. And how do we know whether we are supposed to interpret pi as a symbol in an alphabet or as a numeric pi? Good question, Bakker. For this question, it doesn't matter. So if it were to matter, then we would tell you. Right? For this question, even if it's a string of repeated pi's, it would still be a countable set. Pavon, to answer your earlier question, how do we know that the ratio between two reals don't always give a rational? Divide 2 by the square root of 2. You get the square root of 2, and the square root of 2 is not rational. Okay. Almost break time already. So I was gonna consider skipping this question, but I think it's better to end this topic before the break rather than have 5 minutes of the next topic before the break already. So let's do it anyway. So instead of a set of numbers or a set of strings, I now want to consider a set of functions. Remember, Q is the set of rationals and C is the set of complex numbers. Let's see what you make of this. Okay, let's take a look. Okay, 1/3 for A and 2/3 for B, roughly. So can anyone tell me why B is the right answer? Okay, so we have a variety of answers coming in. But Lynch and also Vilaug and also Andre are pointing to the right answer. We're looking for a set of functions. Okay, also Otto now. Just take a set that contains one function. Or even better, take a set that contains no functions. This set is finite and therefore countable. Right, so even though there are uncountably many functions from Q to C, I think I'm correct in saying that, though I'd have to write it down and check, because reasoning and logic is also half a year ago for me. But is every set of functions from Q to C uncountable? No, definitely not. Take a finite set of functions, an empty set, a set with one element, a set with two elements, a set with any finite number of elements, and you've got a countable set. So no is the right answer here. Okay. Okay. Then we have 2 minutes left until the break. I suggest we do not start a new topic here. So either we'll have our break a couple of minutes early, or perhaps you have a question for me now. Let's see if you have any in feedback fruits. Nope. Can I give an example of an uncountable function from Q to C? Well, that's not what the question, an uncountable set of functions. Okay, there we go. Sure, I think I can. So let me think. Yes, we are allowed to do that. Yeah, let me see if I can get my tablet working for this. That would help. I need to move over some stuff here. I want this to show up. And I want this to be here. Then let me hide this, make this bigger, and do this. Okay. So here we go. an uncountable set of functions from Q to C. Consider the following set of functions. We take a fraction and we return that fraction plus some real number r. Now we can as our set S take, so let's have this depend on two things, all of the all of these functions, if you see what I mean. Then for every real number, or even every complex number if you like, right, have a different function that maps a rational number onto a real number. And there are infinitely many of these or uncountably many of these functions, so the set S is uncountably infinite. Does that make sense? Who asked this question again? Arcade? Good. All right, then I suggest we have a break. I'll stick around in Twitch chat, though I also want to get a fresh cup of water. So if you have any more questions, ask them there, and I'll see you in about 15 minutes. All right, so let's try to get started again. Welcome back. Let's move on to the second topic of today after answering the one question that is still in feedback fruits. So are natural numbers and rational numbers closed under the minus operator? Is x minus y still a countable set? So rational numbers, yeah, for sure. Natural numbers, it's a little bit trickier, right? Because x, y, right? It takes two arguments, x and y, and it returns x minus y, might not be a well-defined function. If x is smaller than y, then fx minus y would be, or f of x equaling, right, let me just write this down. That's probably easier for me than trying to do this all in words. So let me open up the tablet again, which should still work. Yeah, there we go. Not gonna bother making it the right size, so you'll see a little bit of my default Windows background, but that's okay. Right, so if we have a function f that takes two arguments and returns x minus y, and we want f to be this, then that's not gonna work. Because take, for example, f of 3, 5, that would be 3 minus 5, which is not an element of n, right? But if we are a little bit more careful here, and for instance we say, well, f of x is y equals 0 if x is smaller than y, and x minus y otherwise, then we could at least have a valid function here. But this is, it's a bit trickier to say whether the set of all numbers x minus y for x and y in n is countable. Well, it is, but we should be aware that it is no longer a subset of n, basically. All right, let me hide this again. There we go. Okay, and then let's talk a little bit about decidability while I reposition some of these things. Okay, so decidability. Last week we talked about decidability. Now we're going to talk about undecidability. So we're going to ask questions like, is this stuff decidable, yes or no? So in this case, we have a language Y. Y contains all of the context-free grammars that are in Chomsky normal form. Can we decide that language? Feedback Fruits is happy to hear your thoughts. Okay, let's see what you think. Majority for answer A, 75% of the votes. So why answer A? This is decidable, okay. That means we must be able to make a Turing machine that does this. What would it have to do? Zoom says yes, because context-free grammars are a subset of decidable languages. So I guess you mean context-free languages. You're right, but that's not enough. So that would allow us to check whether, or we can build a Turing machine that decides a context-free language. But this is, given a description of a grammar, we need to check whether the grammar is context-free and whether it is in Chomsky normal form. So how could we do that? I'm going to give you a couple more seconds to account for the stream delay, and otherwise I'm going to give an answer. Okay. Pavon is telling us yes, because the rules of CFG and CNF are finite. And Andre also, we can verify each rule that it meets the conditions of the CNF, right? Yeah, exactly. So all we need to do here is verify that our input represents a context-free grammar. Okay, so we need to think of some way to encode a context-free grammar, but we can do that, and we can check whether this matches that encoding. And the second thing is whether it matches all of the requirements on the Chomsky normal form. And there is a finite set of rules that we need to check, okay, does the grammar adhere to these rules? For example, no rules going to the start state, stuff like this. So yes, this is definitely decidable, because given one of these descriptions, we can first check, okay, is this indeed a description of a context-free grammar? And then does it meet all of the requirements of the Chomsky normal form? Again, there is no need to check which words are accepted or rejected by the grammar or anything like that. It's only about this description of G, and we need to check whether the description of G is the description of a context-free grammar in Chomsky normal form. So scanner, there is no need to worry about looping or anything like that. We're never going to simulate this grammar or run this grammar itself. All we're going to do is take a look at the form of the grammar. And that we can definitely decide. All right. Then, that was a pity. Well, pretend you didn't see it. Go and give it a go anyway. Slightly more complicated question. We know that EQ CFG is undecidable. Now we have two grammars. Is it still possible to construct a Turing machine that tells us that these grammars are equivalent? Okay, I'm going to give you a little bit longer on this one. Let's say 10 more seconds or so to give me an answer. If you have one, you may have spotted it on stream when I accidentally double-clicked instead of just clicked. Okay, let's see what those of you that answered think. Answer A is the most popular, and then some for B, some for C. So let's take a look first at what grammars we have. Grammar G1 and grammar G2. Well, take a second, but I'm pretty sure you should be able to convince yourself that both of them accept only one word, namely the empty string, or the empty word. right? Neither can accept any other word. So yes, these two grammars are equivalent. Their languages are the same. However, EQCGF is indeed undecidable. So I can see why many people would say, okay, then that means it's impossible for a Turing machine to decide that these two are the same. However, we can easily make a Turing machine to do so. Just have a Turing machine, and it's similar to what Otto is describing, that checks, okay, is the first grammar I get exactly grammar G1 here? Is the second grammar I get exactly grammar 2 here? And if so, return yes. Otherwise, don't. And that's exactly what answer B is describing, right? So we have a very specialized Turing machine. It does only one thing: check if it's dealing with these two grammars, and if so, accept. In all other cases, reject. Well, that machine will never loop. So it can decide the equivalency of exactly these two grammars. Answer A, however, is not possible because EQCFG is undecidable. So we cannot do this for the general case, but we can, given a description of a grammar, check whether it is exactly grammar G1 or exactly grammar G2. So Amida, wouldn't it get stuck in the BB loop? It will never get in the BB loop. All it's going to do is it's going to take two descriptions of grammars and check whether this description of the grammar is exactly equal to G1, or to the description of G1. And the description of it, the second grammar it gets as an input, is equal to the description of G2. So it doesn't run it on any words or anything like that. So all it does is it's a general Turing machine that takes as its inputs G1 and G2, or takes as its inputs two grammars, and it checks whether these are G1 and G2, and if so, accepts, and otherwise rejects. Pafon, I'm not quite sure what you mean with destroying rules. Tim is asking about, doesn't it tell us that these grammars are equivalent? It only returns whether the inputs are these grammars. Yes, but we have already established that these two grammars are equivalent. So now we can have a Turing machine decide it, right? We're basically pre-feeding the Turing machine with the answer to our problem. Ah, I see what you mean now with destroying rules, Pafon. So even if we have destroying rules, as you coin them, right? So a rule where AA would go to just one A, instead of over here we have B going to BB. I'm still not convinced that it would be possible in that case, but I need a piece of paper to really work that out. But yeah, like Otto was mentioning, in this case that's not relevant because we are never simulating the grammar in any way. So again, the question asks, can we construct a Turing machine that tells us that's the grammar, that the grammars are equivalent? Yeah, we can. It simply checks whether its inputs are these grammars, and if so, it outputs yes. So this is the distinction between EQCFG. For arbitrary grammars, decide whether they're equivalent. That's undecidable. To very specific grammars, yeah, we can. We as humans can figure out for two grammars what are the languages of these grammars, and we can compare them. It's a very creative process, and not one with a systematic method. But if we know the answer, that's how I should phrase it. If we know the answer for two specific grammars, we can encode this into a Turing machine. But for the arbitrary case, Turing machines, nor us, can do it. Okay, let's move on to the next one. Suppose we have a decider for ECFG. ECFG, ECFG. So that's not EQCFG, it's empty, right? So is the language of the grammar empty? And now we have a pair of grammars G1 and G2. How do we decide whether L of G1 equals L of G2? Okay, let's take a look at what you think. About a third for answer E, and the rest is split over the other ones. Now, can anyone tell me why answer E is correct? So answer E is the right answer, but why is that? Yeah, Jonathan, you're right. And also Andre, yes, and Godzilla, great usernames here. Because EQCFG is undecidable, right? So how do we decide whether the language of two grammars is the same? We can't. This problem is undecidable. So personally, I haven't even read answers A, B, C, and D. Whatever it says over there, it just can't be done. So answer E must be the right answer, right? How do we decide whether two grammars have the same language? We can't. Because indeed EQCFG is undecidable. So answer A and B, quarter of you voted for it. They might have ingenious sounding answers, but whatever they say there, it cannot be done. A decider for ECFG, Pavon, if I remember correctly, is possible. I believe ECFG is decidable, but I might be mistaken there. Yeah, exactly. The giveaway is the equation at the end, Wakker? Yeah, indeed. Why is it not B? Nookepook, great name. Well, yeah, okay, so the simple answer is that EQCFG is undecidable, so whatever we do, it can't work. But let's take a look quickly then at answer B. Construct a machine M with an empty language if and only if the languages of G1 and G2 are the same. Yeah, so then machine M needs to decide this problem. Is the language of G1 the same as the language of G2? And it can't, because it's an undecidable problem. So we cannot construct such a machine M. E does not mean enumerator, but empty. And Frostbite is also bringing up a valid argument against answer B. K is a decider for ECFG, so it requires to be run on a CFG, whereas we are constructing a machine, so we can never run K on M. We could only run it on a grammar, not on a machine. Good point, Frostbite. Okay, then let's move on and show that ATM, one of these undecidable problems that you've studied, is actually recognizable. So if we want to show that a problem is Turing recognizable, we need to construct a machine to do so. One of these answers does, and I hope you can tell me which one does. Or if none of them do, then answer E is the answer you should pick. Okay, and let's take a look at your answers. Answer D is by far the most popular. Well done. Yes, so what do we need to show that a problem is Turing recognizable? Well, if a word's in the language, our machine should accept. If a word's not in the language, we don't care, so long as it doesn't accept. It can loop or it can reject. Both are fine, so long as it doesn't accept. So if it's in the language, it should accept. Well, let's take a look at answer D. What does it do? It simulates M on W. It accepts if M accepts. Okay, that seems to be fine. It rejects if M rejects. That's also fine. The only problem that could occur, if W is not in the language of M, then M might loop, and therefore M4 might loop. Okay, that might be, or that's why this thing is not a decider, but it is still a recognizer, right? Any word that is in the language of M will indeed be accepted. Or will force M4 to accept, I should say. So answer D is indeed the right answer. Does that make sense? Are there questions about that? Give you a couple more seconds to type up a question if you have one. Otherwise, I'm just going to continue. Could I repeat the reasoning? Yeah, sure thing. So once more, for Turing recognizable, to show something is Turing recognizable, we need to construct a machine such that when a word is in the language, we should accept, and when a word is not in the language, we should reject or loop. So what does answer D do? Well, given an input of a machine and a word, we simulate the machine on that word. Now, if this machine accepts this word, right, so m, w is in ATM, then our machine will accept, so we will get to step 2, and we will accept, because m, w should be in ATM. However, if w is not in the language of m, meaning m, w should not be in ATM, then step 1 might loop. But that's no problem, because for recognizability, we need only a machine that accepts for inputs that are in the language, and for inputs that are not in the language, we may loop or reject. So if step 1 loops in that case, that's not a problem. I've tried to explain it using a slightly different way. I hope that helped. It seems to have. Okay, good. Then, now let's talk about ETM. And I want to know which of these TM proves that ETM is co-Turing recognizable. All right, let's take a look. Ooh, very, very well spread. Okay, okay. Let's take a look at answer A first, with a third of the votes. Construct an enumerator E for M. Simulate E and wait until a word is printed. If a word has been printed, accept. So what does this do? Well, we make an enumerator. Okay, an enumerator. How could we do that? Well, we saw this last week, right? For any machine, we can construct an enumerator by first running it for one step on all words of length 1, all words in sigma star of length 1, then run it on all words of length 1 and 2 for 2 steps, run it on all words of length 1, 2, and 3 for 3 steps, of all words on length 4 on 1, 2, 3, and 4 steps, and so on and so forth. So okay, we can construct such an enumerator, we can simulate it, and then wait until a word is printed. If a word has been printed, accept. So what happens here? Well, if the language of M is indeed empty, then this machine would loop. However, if the language of the machine is not empty, then at some point a word will be printed, and therefore our machine will terminate. So indeed, this thing is able to recognize any machine that is not in ETM. So I'd argue answer A is the right answer. Any machine whose language is not empty will be recognized by machine M1. So co-Turing recognizable Taylor indeed means that the complement of the language is Turing recognizable. So everything that is not in ETM we can recognize. Let's take a quick look at answer C, which was also quite popular. On an input, simulate the machine for every word in sigma star. If it ever accepts, accept. Well, the problem here is that step 1 could loop, right? It could loop on the very first word, and then it's never going to do anything. So imagine that the first word in sigma star is A and the second start in sigma star is B. It rejects both, or it loops on both, whatever you want. Then this is going to be fine, because the language is empty, we don't care. But if it loops on A, but doesn't loop on B, then by simulating the machine for the word A, this thing will loop, even though when running it on B, we find that actually it shouldn't be in ETM, because it would accept B. So we really need to do this whole dovetailing again, right? Where we do 1 step on this, and then 2 steps on the next, and then 3 steps on all, etc., etc. And this is not clear from the step 1 here. So if we were to parallelize the simulation or dovetail it in some way, then it could work, but that's not in our answer here. It simply says run it on every word. Does that make sense, Jonathan? So again, scanner, if we have the word A on which it loops, and on the word B it would accept, we would never find out that it accepts B, because we would already be looping on A, and therefore machine 3 doesn't recognize that machine as not being a part of ETM. All right, so answer A was indeed the right answer. One more, I think. Yes. Let's see if we want to skip this one. No, we can do this one. So how do we show that every infinite Turing recognizable language contains an infinite decidable subset? Right, so we have infinitely large Turing recognizable languages. Now I want to show that every single one of these contains at least one decidable subset that's also infinite. How could I do that? All right, let's see what you think on this one. Again, nice spread of answers. Getting into the trickier questions now. Someone remarked, I think it was Frostbite, yeah, B and C seem similar. So let's first take a look at what the difference is between those then. So the question asks that every infinite Turing recognizable language contains an infinite decidable subset. Answer B. An infinite Turing recognizable language can be enumerated. Let's think. Is that true? Yeah, we can enumerate a recognizable language. Okay. Taking the elements from the enumeration that form a monotonous sequence yields an infinite decidable subset. Okay, a monotonous sequence means that every element that comes after it must either be larger or every single one must be smaller, right? And this repeats. So for example, monotonous functions are functions that always increase or always decrease. And similarly, we could have that in our sequence, for example, if we use dictionary order. Okay, so that's what answer B says. What about answer C? Sort the Turing recognizable language and enumerate the sorted list. This enumeration forms the desired infinite decidable subset. It does indeed look very similar, but in order to sort it, we somehow need to know all of them. And that might be very tricky, right? Sorting an infinite set, how would that work? Well, it requires us to know at least all of the ones that are in there. So answer B works a little bit more out of the box, let's say. And we've got a nice proof for that. So let's quickly go through that. What can we do? Well, since L is recognizable, we must be able to construct an enumerator, right? So what do? We simply start enumerating. And now we create an enumerator for such a subset that will be decidable. What do? Well, run it on all the, or run the original enumerator. And now every time, check whether the words that this enumerator is giving us, check whether that word is larger than the previous word, where larger again could be lexicographical order or whatever we like. Some ordering. If it is, great, we also print it, so we also enumerate it, and otherwise we don't. And now we have something that only prints them in this specific order, which means that it's decidable, as we saw last week. And so we can indeed create an infinite subset that is decidable for every infinite Turing recognizable language. Well, Frostbite, I'm not entirely sure. Consider, for example, a to the power n for a natural number. That one we can easily sort, right? Even though it's infinitely big. It's a, and so on and so forth. So I'm not sure whether it's true that any infinite language can never be sorted. But I'd argue that there are definitely ones that we could not. Yeah, maybe we can. So the problem would be, I suppose, let me go back, that finding the language, right? Our enumerator will run forever. And so since our enumerator for a Turing recognizable language doesn't have to be in alphabetical order, it means that that's the reason we can never sort it. We could create an enumerator for a recognizable language, but this will give us to them in any order. But we can never make sure that there is nothing going to be in between two words, because our enumerator might still at some point mention a word that goes in between, if that makes sense. Okay, let me take a quick sneak peek. Yes, let's do one more. So let's do this one. It's the same as the previous one, only now there is an answer that works. So we first gave two answers that both don't work. Let's go immediately to one that will work. So we have a Turing recognizable language B that contains a whole bunch of machine descriptions. Can we now construct a decidable language such that for every machine in B, there is an equivalent machine in C? I'll give you 2 minutes to give me an answer in feedback fruits. Okay, let's see what you've made of this one. There we go. 35% for answer D, 30% for B, and another 36 combined for A and C. So C, let's start with that one, looks very similar to what we just saw, right? And so therefore you might be tempted to pick that one, and some of you did. Unfortunately though, if we only take the ones that form an increasing row, then we don't have something for every machine in B. So answer C doesn't work for that reason, right? For each machine in B, we want an equivalent machine M prime to exist in C. Let's take a look at answer B then. By forming an increasing sequence, which is decidable, by supplementing the descriptions in B, for instance with unreachable states, or by expanding the tape alphabets, independent of representation. This way they stay equivalent, but C becomes decidable. Yeah, so this is exactly what we could do, right? So M1 we put as it is as the first thing for our enumerator for C. Now, for M2, if the description of M2 is shorter than the description of M1, then we need to pad it a bit. So we can throw in some unreachable states, we can throw in some extra tape symbols that we will never use, whatever works just to pad the description size. And then we can print this modified machine that is still equivalent. And for M3, again, if it's shorter than the description of this padded M2, then we need to pad M3 even more. So throw in even more unreachable states, throw in even more tape alphabet symbols that we never use, whatever works, just to make sure that this padded M3 becomes larger than our padded M2. And now we have created a language that contains equivalent machines to the ones in B, but that is decidable. So in order to create such an increasing sequence of machines, the best thing we can do is to look at the length of their descriptions, because that's something that we can easily compute. The size of their language, for example, we cannot, remember, because ATM is undecidable. But the size of their description we can easily see. Put it on a tape, count the number of symbols required to represent it. So to form an increasing sequence of machines, we can form an increasing sequence of descriptions. I hope that answered your question as well, Pafon. Okay, I see no new questions in Feedback Fruit, so I'm going to send us off into another break, and we'll be back about 15 minutes from now. I'll stick around a little bit, answer some questions in Twitch chat during break if there are any. And then I will see you in a bit. All right, once again, welcome back to the last part of the lecture today. Thanks again for sticking it out with me here on Twitch. Still realize this is not the ideal setting for a lecture maybe, but we're making it work and you're behaving very well in Twitch chat today. Thank you very much for that. It makes interaction with you possible and I really appreciate that. So thank you all around. All right. Let's delve into that last bit of today. Let's talk about reductions. Now, unfortunately, reductions is one of those topics that is a bit hard to do in one of these sessions because asking multiple choice questions about reductions, although definitely possible and will do some, isn't quite the same as doing some full reductions on your own. So again, I strongly recommend you check out assignment 6 in which you do one of these reductions by yourself. Doing a full one of these reductions is definitely a better way to practice them than by looking at these questions. Okay, that being said, let's at least discuss a little bit what the idea of these reductions is. So here we go with the first question. What's the idea behind direct reduction of a problem A to a problem B? 2 minutes might be too much for this one, but we'll see. Maybe I'll cut you short after a minute instead of after 2. All right, let's say 10 more seconds, and then we're gonna take a look. All right, let's see. Overwhelming majority for answer A. A can be solved using an algorithm for B. Yes, that is exactly the point, right? If we reduce A to B, then that means that given a solution to B, we can also solve A. B is definitely not true, right? This doesn't work the other way around. For that, we would need a reduction from B to A. Answer C, it is known that B is decidable since reductions are computable. No, because if we take an undecidable problem, then this doesn't work. It is not known that A must be, so if A is undecidable rather, then answer C wouldn't work. It is known that A must be at least recognizable because A is a subset of B. No, so reductions do not talk about subsets. So this is also false. For example, when we reduce, is it ATM to EQTM or something like this? One of the first reductions done in the book. I'm not quite sure what it is, but I'm pretty sure that the inputs are different and therefore that definitely can't be a subset. Okay, good. So yeah, just to repeat, why do we repeat this? Well, because next week when we talk about complexity theory, we will also be talking about reductions, only things called CARP reductions. But they have very similar properties, right? So if A can be reduced to B, that means that a way to solve B yields a way to solve A. And if there is no way to solve A, there is no way to solve B. And we will see very similar properties next week when we talk about CARP reductions in the context of complexity theory. The notation is also the same in complexity theory. We use the smaller or equal symbol. And indeed, you can interpret that as A is easier than or as hard as B. In complexity theory, we prefer A is not harder than B, but that's the same thing. Okay, good. Then let's do one or two more of these. So, did I want to do this one? No, I wanted to do this one. Yes. So the others, I considered also getting them out of the PDF, but since we published the PDF, I figured I could leave it in. You can take a look later. But there's only a few I want to discuss now. Like I said, the multiple choice format isn't always great when talking about reductions. But a little bit of time to think about this one. All right, let's see. And let's see what you think. Answer A is the most popular with almost half of the votes. Still a quarter for D. Let me start by pointing out one small thing from chat. So let me go back to this one. So we write A smaller or equal to B to represent A can be reduced to B. So Sphinx, you were saying it might be the other way around. This is not the case. A smaller or equal to B means that A can be reduced to B. Okay. Then let's look at this one. So I already spoiled this, so I might as well show it. Yeah, so one of the techniques that we used to find our very first undecidable problem, ATM, was the technique of diagonalization. We could do something similar for all the others. Problem is that that is often not the easiest method. It is much easier to do a reduction starting from an undecidable problem and then derive a contradiction. So that's why we prefer these reductions, but you could technically also use a proof by diagonalization to show that a problem is undecidable. After all, that's how we found our first undecidable problem, ATM, that we have since been using as the basis of these reductions. So other ways exist, but are not recommended. Answer D says even against reduction, there are counterexamples. Check this. And Frostbite already said that check this might be a hint. It isn't. If we find a reduction, that's good enough as a proof. There is no counterexamples against reductions, only against invalid reductions, of course. Okay. Okay, then let me see again. There was one more I think I wanted to do here. Yes, it was this one. Yes. So this is back to decidability for a little bit. Is it possible to decide that halt PDA, or is it possible to decide halt PDA, where halt PDA is given a PDA and a word, the PDA halts on that word. And again, I'm going to cut us short here because many people seem to have answered it already. So 5 more seconds to give me an answer if you have one, and then we take a look. Okay, let's see. Ooh, almost 50-50. Very nice, very nice. Okay, well, can anyone tell me if this is decidable? That means we must be able to create a Turing machine for it. So how could we do that? So why might the answer be yes? Taylor so far is giving us a reason as to why it should be no. Taylor indicates the halting problem is undecidable. I agree, the halting problem for TMs is undecidable. But this is the halting problem for PDAs instead of for TMs. Perhaps they are different. So indeed, as Jonathan also points out, the halting problem is undecidable for Turing machines, but perhaps for PDAs it is not. Does Rice's theorem come into play here? Not yet. 2 questions from now we'll look at that, but we can't quite use it here. We can just, Pavon is very, very definite in his answer. I say his, but I think I'm right in this case because I think I know who Pavon is. PDA can be run on W in finite time because a PDA must always halt. Well, a PDA, the problem with that thing is that it is a bit non-deterministic. So for a deterministic Turing machine to do it would be a bit harder. But for a non-deterministic one, sure, that would maybe work. Alternatively, I would say, well, how about we just convert our PDA into a context-free grammar, right? If you want, you could even translate that one into Chomsky normal form, but I don't think you really have to. And we know that ACFG is decidable. Right, so the question, given a context-free grammar and a word, does the grammar accept the word? This we can decide. So then we can also decide it for our PDA. So the answer is indeed yes. So we just convert it to a context-free grammar, and then we can use marking, as Times is saying, to decide whether it halts or not. Okay. Could a PDA loop? Yeah, sure thing. Consider a grammar with the rule B goes to 2 times capital B. So capital B goes to 2 times capital B. this one will loop forever, right? As soon as we have that in our PDA encoded properly, our PDA could loop on that forever. All right. And there was one more here I wanted to do. So these are all very similar, but I wanted to talk a little bit about Rice's theorem, which already popped up just now in chat, but I want to talk about it in a bit more detail. So let's start by discussing Rice's theorem as it is here presented here. So we've seen reductions as a nice way to show that a problem is undecidable. But for many problems, it turns out we don't even need a reduction. We can simply use Rice's theorem. So what does it say? Well, and this is something that should have been in your preparation materials, but due to an oversight on my part, it wasn't, which is why I'll be discussing it in a bit more detail now. I'll make sure that the slides are available. They're currently in week 8 instead of in week 6, so I'll move them after the stream. What is Rice's theorem? It says that if we take any set of Turing machines with a very special property, namely that being an element of this set is only determined on the language you accept. So we can define them exclusively, as it says here, in terms of input and output behavior. So a machine is in there, or if a machine is in there, then any other machine that has the same language is also in there. And if a machine is not in there, then any other machine that has the same language is also not in there. Furthermore, P should not be trivial. So there should be at least one machine in P and at least one machine not in P, right? So P shouldn't be empty, and also P shouldn't be all possible machines. So the complement of P shouldn't be empty. Now, if our set P adheres to these special requirements, then P is undecidable. This is the theorem. There is a proof for this theorem in the slides that I will share later. But the theorem itself the theorem itself is very crucial in showing that some problems are undecidable. Because as soon as we have one of these sets of machines, and being a member of this set only depends on your language, and the set is not trivial, then this is undecidable. So let's do a question to practice with that. Consider the language L, which is the set of all machine word pairs such that the machine accepts the word. Can we now use Rice's theorem to show that this set K is undecidable? Let me open it up in feedback fruits as well. Here we go. And I'll give you a bit of time to think about it. Only 2 answers in feedback fruit so far. Let's see if we can make that a little bit more. Though I realize springing something new on you might be a bit more challenging. right. Let's see what you think. I should click here. Some more are coming in now. 36% for answer A, 25% for answer E, 20% for C, and some split between B and D, but overall also a lot of non-answers. So perhaps it's good to discuss this one in a bit more detail. So Rice's theorem says that if two machines have the same language, then either they should both be in our set or both not be in our set. Or rather, that's one requirement, right? So if this requirement is satisfied, then the language is undecidable. Let's take a look at language K. Consider two machines, M1 and M2. Now let's say that their languages are equal. If M1 is in K, then the language of M1 is a subset of L. Now, since the language of M2 is equal to the language of M1, the language of M2 must also be a subset of L, and therefore M2 must also be in K. Similarly, if the language of M1 is not a subset of L, meaning M1 is not in K, then since the language of M2 is equal to the language of M1, it must also not be a subset of L, so it must also not be in K. So this first requirement of Rice's theorem is satisfied. Furthermore, we need to show that there are machines that are not in K. Well, that's trivial. Take, for example, the machine that accepts sigma star. Its language will not be a subset of L. And we need to show that there is at least one machine in there. Again, that's trivial. Take a machine whose language is the empty set. And that one will be in K, because the empty set is a subset of L. So both of the properties of Rice's theorem are satisfied. And so we can indeed use Rice's theorem to prove that the language is undecidable. So it must be answer A or B, or if they contain a mistake, then it must be answer E. Well, let's take a look. Answer A, yes, in the definition of K there is no explicit talk of words, but that is not a requirement. Consider, for example, and let me see if I can set up my tablet again. Does this work? Yeah, my tablet went into lock screen mode, but you should now, after this, yes, no, maybe. There we go. Consider, for example, the following language. Descriptions of machines such that M accepts the word Phoenix. This does have an explicit mention of words, but still we can apply Rice's theorem to it. Because again, if the language of two machines are the same, then both must be in L or both must not be in L. So the fact that there is no explicit talks of words is not good enough to say that we can immediately apply Rice's theorem. So answer A is not correct. Answer B talks about stuff being decidable, whereas we want to show something is undecidable, so I'm not quite sure how answer B would work at all. So answer C in this case is the correct answer. Sorry, answer E in this case is the correct answer. With the extra bit of information added that the language is undecidable because it does satisfy the requirements of Rice's theorem. Does the undecidable part of Rice's theorem relate to the fact that we can't tell which one of the machines we are using? Asked by Nuke. Or what exactly does undecidable mean in Rice's theorem? So Rice's theorem is so normally we can use reductions to show that a language is undecidable, right? Now we can also use Rice's theorem So it's the same notion of undecidability. And it says that any set of Turing machines, so a language containing descriptions of Turing machines, is undecidable if these two criteria are satisfied, Nuke. And that means that the set of machines is exclusively defined in terms of input-output behavior, meaning two machines with the same language are either both in our set P or both not in our set P. If that is the case, and also P is non-trivial, then P is undecidable. Perhaps it helps to take a look at some more examples and see which one we can and which one we cannot use Rice's theorem for. So the question should be open in feedback fruits now. I'll give you about 2 minutes. See if you can decide which of these languages we can show to be undecidable using Rice's theorem. All right, let's take a look. Answer C and D are both very popular. Let's see what they have in common. They both seem to agree that answer 2, or the second language, is true. The statement about the second language is true. The statement about the third is the one they disagree on, and the first one must be false. Okay, so let's quickly knock out the first one. L-min halt. It's all the machines where the machine is a Turing machine and halts in a minimal number of steps on every input. Well, this is not about the input-output behavior, right? So indeed, we could have two machines with the same language, but one could be in the set L-min halt, whereas the other one is not. So just knowing the language of a machine is not enough to conclude whether it is or is not in this set. All right, two machines with equal language, one could be in, one could be out. So this indeed does not satisfy the criteria of Rice's theorem. The second, you also seem to agree on that it must be true. So let's see. The language LR, M is a Turing machine and LM is a subset of LA star B star. Yes, this is very similar to what we've just seen, right? Again, take two machines, M1 and M2. If their language is the same, well, then either both of them are a subset of A star B star, or their languages are both not a subset. So either they are both in there or they are both not in there. So this criterion of Rice's theorem is satisfied. The second criterion is also satisfied because we can trivially make a machine that is in here. Again, take for example the machine with the empty language. And we can also trivially make a machine that is not in there. For example, take the machine with as its language only the word C. That is definitely not a subset of A star B star. So statement 2, true. Now statement 3 is where the disagreement arises in your answers. LM is countable, is the criterion we put here. Well, again, okay, take two machines. If their languages are the same, then either they are both countable or both uncountable. So, yeah, either they are both in there or both not. Now let's see about these other properties. There needs to be a machine that is in here. Again, that's fair. If the machine is in here, then, or give a machine that's in here, again, take a machine with the empty language. Empty language is finite and therefore countable. Now we need to come up with a machine that is not in here. So we need to find a machine that generates an uncountable language. Can we do that? Can we create a Turing machine whose language is uncountable? Anyone have an idea? A machine that accepts all input, Pavlon suggests. Okay, let's think about that. So a machine that accepts all inputs accepts sigma star. So is sigma star uncountable, is then the question. Well, sigma star is infinite for sure, but sigma star is also countable. How do I know? Well, I can list them. And if I can list them, I can count them. I start with all the words of length 1, then all the words of length 2, then all the words of length 3, then all the words of length 4, and so on and so forth. Admittedly, creating the bijection from n to sigma star isn't trivial, but I hope you can see that we can apply this ordering. There's always a next one to be defined, and this is yeah, exactly. So Otto is suggesting the thing I was trying to explain. So indeed, take the dictionary order of sigma star, and then the bijective function is simply the index in the dictionary order. It's hard to write that as fx equals something, but indeed in English it's easily described. So that means that whatever Turing machine we've got, its language is always going to be countable. Meaning, whatever Turing machine we've got, it's always going to be an LC. Meaning, this thing is very easy to decide. A decider for this would just check, is the input a Turing machine? If so, accept. Otherwise, reject. So the correct answer is therefore answer C. We can only apply Rice's theorem on the second one, not on the third one, because it is a trivial language. Every Turing machine is in it. So once more, to apply Rice's theorem to the third statement, we need to show that it is a non-trivial set of Turing machines. That means we need to show there is at least one machine in there. Well, this we can easily do. Take a machine with the empty language, for example. The empty language is finite and therefore countable. We also need to show that there is at least one Turing machine that is not in the set L, in the set LC. And that is impossible because any Turing machine will have a countable language, because its language will always be a subset of sigma star, and sigma star is countable. So indeed, Jonathan, it is impossible for a Turing machine to have an uncountable language. Because they are subsets of sigma stars, they must be countable. Although we can't have an alphabet of real numbers, our alphabet must always be finite. So it's impossible to have an alphabet of all the real numbers. Okay, you already suggested that at the end of your question. I only read the first sentence and then I stopped reading. I should have read the whole thing. Yeah, okay. Good. Um, Now, that was all I wanted to discuss today, which means we have 10 minutes left, which is excellent. Let's see. Because I wanted to already give you a tiny sneak peek at what we're going to do next week. So next week and also the week after, we are going to take a look at complexity theory. Now, complexity theory is a subject that I really, really love. And to me, it's still a great pity that this is going to be removed from the curriculum. I'm very happy that I can still teach at least 2 lectures about it to you next week. And I want to introduce it a little bit by giving you a little bit of the talk that I usually give at the open days for computer science. Because you've been here for 2 years now, and we've taught you a lot of things, right? So in reasoning and logic, we taught you how to prove stuff like this, because you could do this using induction, by using a lot of English and a lot of mathematics, and then using more English and more mathematics. Then in courses like algorithms and data structures and algorithm design, we talked about stuff like this. Given a graph, how can I find the shortest route? And you now know how to implement Dijkstra. You now know how to find minimum spanning trees and all this kind of stuff. But everything we did over there was about problems that have what we call efficient solutions. And now that you've done all of that, and that now that you've gone through the first the first 3 quarters even of Automata, you are ready for what I would describe as the ultimate challenge in computer science. Now, if you ask other people, if you ask Andy, maybe even if you ask Matthijs, they will probably give you a different ultimate challenge in computer science. That's okay, we all have our own favorites. But to me, the ultimate challenge in computer science requires you to imagine that you are this guy. You are what we call a traveling salesman. You travel the lands, buying and selling your wares everywhere you go. But, like everyone, you come to one inevitable conclusion. There is one city more beautiful than any other. One city truly worth spending your time in. And so, you now ask yourself this: how can I travel the land, going to all these other cities, and get back to Delft as quickly as possible? If you just want to go from Delft to another city, you know that you could use Dijkstra's algorithm to find the shortest route. But now I don't just want to go to one other city, I want to visit all other ones and get back to Delft as quickly as possible. One strategy you could use is this one. Always take the shortest route available to somewhere you haven't been before. Now in a moment, I'm going to give you a minute to apply this strategy. See if it gets you the shortest route home. But then I want you to do something far more important. I want you to break it. Change just one number so that this strategy doesn't work anymore. And if you have a bit of time left, why not try and think of a strategy that always works? No matter what the numbers look like, a strategy that always finds you the shortest route through all cities and back to Delft as quickly as possible. So 1 minute to apply this strategy, to break it, and to find me one that always works. And if you find one, I've got a very big prize waiting for you. So let's see how this goes. All right, so let's figure this out. If we apply this strategy, we start by selecting from the 2, the 3, and the 7. We take the 2. Now we pick between a 4 and an 8. So we pick the 4. Up next is 7, 4, 6, 4, 5, and 3. And so we've done it. We found a route to get us through all the cities and back to Delft. But is this the shortest route? Well, if we were in a lecture hall, I'd ask for a quick raise of hands. And hopefully, at least this is always what happens on the open days, many of you wouldn't know, because you've been so absorbed in applying this strategy that you forgot to check whether it actually works. Of course, you're second-year computer scientists, perhaps a better informed crowd than the open day crowd. Now, is this the shortest route? Yes. How do I know? Well, if we take a look at the ones I did not select the 7, 2 8s, a 9, and a 10. And if we take a look at the ones we did select, the largest one in there is a 7. So there's no way I can take one of the routes I selected, replace it by one of the routes I did not select, and somehow end up with a smaller total. We can only make it bigger. But I asked you to break it. So let's see if you did. Lich already pointed out one way to break it. If we make the 10 a 1, what's going to happen is that over here we will go via this path, and then either we'd go back to Delft too early, or maybe we would continue along our way and end up over here. Stuff would go wrong regardless. Zoom is thinking, okay, what if we just add a new node? That might make it go wrong, but Jonathan has the answer that I also have on my slide, except with a slightly smaller number in my case. How about we make that last 3, for example, 30,000? That's guaranteed to break it, right? Whatever happens, this surely isn't the correct path anymore. Now I asked you to find me something that always works, and again, Jonathan fortunately did. He says, okay, why don't we just try all the options? And of course we can, right? So now let's imagine there are n cities. We can go from any city to any other city directly, meaning we have n minus 1 options in the first one, n minus 2 in the second one. That means I have the faculty of n options in total. Well, technically the faculty of n minus 1, but trust me, the minus 1's not going to matter in a moment. Now, even with an incredibly fast computer, something that could check 1 billion options a second, just for 36 cities, it would take longer than the age of the universe to check all the options. So clearly, although trying all the options technically works, and it means that this problem is definitely decidable, right, in our context, it doesn't mean that it's a strategy that is feasible for us to use. And that's what complexity theory is all about. And that's, to me, the ultimate challenge in computer science, and we call it P equals NP, ? Next week, you will know exactly what these terms mean, but very simply put, it is the simple question, given a bunch of cities, is there a strategy that will find you the shortest route through all cities back to Delft that is feasible, that we can compute for large values of n? And in computer science, of course, we don't really like the answer I don't know. We love the answer it depends, but I don't know is not something we tend to like. Unfortunately, that's the best answer we've got here. P equals NP is still an open problem in computer science. And for the next 2 weeks, I'm only going to talk to you about the current state of the art. But the current state of the art doesn't have all the answers. We don't know whether P equals NP. And that means that there's 2 options. On the one hand, someday someone might wake up who will show the world that yes, there is an efficient strategy to find the shortest routes through all cities, and we have been incredibly stupid so far. Well, as a computer scientist, I don't really like that option, because that would imply that I've been incredibly stupid so far. The alternative is that there is no efficient solution. But if there isn't, then why can't we prove that? Well, I'd like to show the world that we're not stupid, but I can't do that either. So we're stuck in the middle. Every day someone might wake up to shame us, or someone might wake up to save us. And that is the problem of P equals NP. Now, on the open days when I tell this story, many of the prospective students get into moods like this. Hopefully, after studying here for 2 years, you've become a little bit more tolerant to stories like this. Perhaps, though, I can give you a reason to care. I told you that if you solve it, I'd give you a big prize. And I would. $1 million. One way or the other. If you show that we've been incredibly stupid and that it can definitely be done, come talk to me first. We can make that $1 million a whole lot more. And if you show that, yes, computer scientists so far haven't been all that stupid, it really is impossible, then you'll get $1 million all the same. Now, is that why you should study complexity theory? To get your shot at that $1 million? Of course not. This is why you should study complexity theory. And next week, we're going to take a look at a whole lot of these nice problems. Problems that are decidable, problems that have solutions. But for us to figure out what these solutions are is something that we cannot efficiently do. And we are going to try and look how we can show that some problems are easier than others. We're going to see that all the problems you've encountered so far in algorithms and data structures and algorithm design are what we call easy problems, even though you and I might disagree on the definition of easy in that case. And that there are problems so much harder, problems for which we have no efficient algorithms. And those are the problems we encounter most in our day-to-day lives. So, I'm really looking forward to next week when I get to tell you way more about this, and I hope that after this, you are looking forward to it at least a little bit as well. So with that, I'll see you next week when we talk about complexity theory. See you then.